This video still talking about limits, and we got a theorem here called the Squeeze Theorem to help us out when our other methods of finding limits might seem problematic. Let's take a look at what this theorem is and see how we can use it. All right, here's the theorem. We're first going to state it, and then we'll look at a picture to help us visualize what it means. The Squeeze Theorem. We got three functions. Suppose we got three functions, f of x, g of x, and h of x. And they all satisfy this inequality right here. And that is f of x is less than or equal to g of x. And g of x is less than or equal to h of x. So basically you have these three functions, f, g, and h. And g is quote-unquote squeezed in between the two other functions, at least for values of x, quote-unquote, near the location of x equals a, except not necessarily at x equals a. So if that's the case, okay, and then you also have that the limit as x approaches a of the lower function f of x is the same as the limit as x approaches a of the bigger of the functions h of x, suppose both of those limits equal the same real number L, then it must be true that the limit as x approaches a of g of x is also equal to L. So visually, try to get an idea of what this means here. Okay, let's take a look at this graph. In this picture, what we see is three different functions. The orange graph down here, f of x, the blue graph, h of x, and then the green graph, the function g of x. So as we can see that when we are nearby x equals a, kind of think about on this little interval right there, the function h of x has values bigger than or equal to g, and the function f of x has values less than or equal to g. And so those conditions of the inequality from the theorem, that f of x less than or equal to g of x less than or equal to h of x, that condition is satisfied, at least for values of x near a. And notice in the picture, what it's trying to show is that as we approach x as a from both sides, h of x, as we see, is approaching the number L over here. Moreover, f of x is also approaching that same number L. And because g has to have values in between f and h, then it must be true that the limit as x approaches a for g of x is also L. Otherwise, if it wasn't, what that would mean is that the value of g is either bigger than h or smaller than f, but that will contradict the statement that we are assuming to be true in the conditions. So it's not a proof, but it hopefully it helps kind of justify why this theorem is true. So the usefulness of this is sometimes we have limits that we might want to try to find algebraically, and we don't really have a good algebraic method of doing so. And so this provides us an alternative to such situations. So what we're going to do now is take a look at an example of how this can be used. All right, what we're going to try to do here is find this limit. Limit as x approaches 0 of x squared times sine of 1 over x. Now, in this situation, we notice that as x approaches 0, right, x squared approaches 0. And also, as x approaches 0, 1 over x approaches some undefined number, right? This approaches undefined. And in fact, it blows up to infinity or negative infinity as we get really close to x is 0. So the concept of limits going to infinity or negative infinity is actually in an upcoming video. So I don't want to really explore that idea right this second. But you think, well, if it is blowing up to infinity or negative infinity, what happens as sine of that amount of stuff? Well, sine is a sinusoidal function, obviously, and it just oscillates between -1 and 1. And so we might suspect, because sine always has values between -1 and 1, that perhaps this limit might approach 0 times some real number between -1 and 1, and hence maybe approaches 0. But, that's just our conjecture here. Now we try to think, well, if we're going to try to find this limit using methods that we've previously discussed, how would we do such a thing, right? We saw some algebraic techniques like factoring if there's a removable discontinuity, or multiplying by 1, like multiplying by a conjugate, or simplifying an expression. There doesn't seem to be a trivial route here to come up with an algebraic technique of finding this limit. And so we say, well, we think maybe this limit exists, without looking at the graph, of course, to help us. But how are we going to do it? How are we going to show this? And that's why Squeeze Theorem comes into play here. So what we'd like to do, the goal for a situation like this, in using the Squeeze Theorem, is find two functions. Think of them as f of x and g of x, so that we have that f of x is less than or equal to x squared times sine of 1 over x, and h of x is bigger than this, and the limit as x approaches 0 of f of x is equal to the limit as x approaches 0 of h of x. If we could find two functions f and h such that that's true, I accidentally wrote g of x up there, it's f h of x, then we would be able to then apply the Squeeze Theorem and can conclude that x squared times sine of 1 over x is actually the same thing as these two other limits of f and h as x approaches 0. So we think of x squared sine of 1 over x as like our g of x, the one that's squeezed in between the two others and satisfying the conditions of the Squeeze Theorem. And thus, how are we going to start with this? Well, one thing we can do is try to come up with some initial inequality that is apparent based on some part of the function that we have given here. So that's always kind of a first goal, is can we come up with some type of inequality that's true, at least for some part of the function, some factor of the function. And in this case, we do have a sine function in our limit, and we know, like we previously said, that sine functions, at least in this form, are always between -1 and 1. So we know that sine of 1 over x in magnitude is always going to be less than or equal to 1 for values of x that are non-zero, because then it wouldn't be defined there. And really what that's saying, right, the same thing, is that -1 less than or equal to sine of 1 over x is less than or equal to 1, again for values of x non-zero. So we kind of have a first step here in constructing the goal of having our function that we're taking the limit of trapped in between two other functions. Now we're not quite there yet, right, because we still have that x squared that needs to be attached. That middle function in this inequality needs to be the x squared times the sine of 1 divided by x. But this is a compound inequality, and for values of x that are not 0, we know that x squared is going to be positive. And hence I can multiply all terms in this compound inequality by x squared, and it results in negative x squared less than or equal to x squared times sine of 1 over x less than or equal to x squared. And that's because x squared is positive for values of x that are non-zero. 0. And so I don't have to worry about, like, if I'm multiplying by a negative number, my inequality symbols get reversed. That's not going to happen here because I know x squared is always going to be positive for non-zero x. And we don't need to consider x being 0 here because we're letting x approach 0 arbitrarily close. So now we got these three functions. Here's our function of consideration, call it g of x. Think of x squared as h of x, and think of negative x squared as our f of x. So we got this function that we're taking the limit of, x squared sine of 1 over x, and it is trapped in between these other two functions, negative x squared and x squared. So that part of the squeeze theorem is satisfied. The question is now, does that other part, the limit as x goes to 0 of f of x and the limit as x goes to 0 of h of x, are those both the same limit? Well, off on the side over here on the left, let's take a look. Limit x approaches 0 of negative x squared, well, that's just 0. Right? That is a polynomial function, and we have previously discussed that when you have a polynomial function and you're taking the limit as x approaches a real number, just plug in that real number into the function. Also, limit as x approaches 0 of x squared, also 0 for the same reasons. And hence, by the squeeze theorem, we can conclude the following thing. By the squeeze theorem, it follows that the limit as x approaches 0 of x squared times sine of 1 over x has to also be 0, because all of the conditions of the squeeze theorem were satisfied, and that's the result. That's the conclusion. So it's not a trivial process. It all depends on the situation you're given. If using the squeeze theorem, kind of think of it as a last result when your other methods of finding limits are not going as planned. And we can always attempt to use the squeeze theorem, assuming that we can construct the conditions in the theorem so that we can conclude the result. Now down here, just to finish the video real quick, here is graph of the situation. That green graph that we see, that's our function that we're taking the limit of, x squared times sine of 1 over x. And then we got the bigger function, the blue graph, y is x squared. And then the lower function, the orange graph, y is negative x squared. And as we can see, as we're getting close to 0, both of these functions, x squared and negative x squared, are approaching 0 as well. And our function, x squared sine of 1 over x, is trapped in between these functions near the location of x is 0 and also has the same limit. So that should all be consistent with what we just concluded above, and indeed it is. So it's just another tool in the toolkit for finding limits, but not necessarily an approach that you want to begin with necessarily on a limit problem, but can be used if our other methods are not going as planned. So that's it for squeeze theorem. Next videos are going to be focused on limits involving the concept of infinity. So stay tuned for those. And until then, I'm out. Math and Beats.